Okay, so in this video, we're going to go into some properties of dimension, right? And in general, we're going to look at what that tells us about determining about the size of a basis and what to check for, right? So previously, to verify if we have a set B and we wanted to determine that it was a basis, we needed to check two things, right? One, that it is linearly independent, and the other is that it spans the vector space. Right, now this second one here can be a bit of a challenge, right? As we saw when we had to set up our system of equations where we just had a general term in the vector space, whether it be a polynomial or a matrix, right? We had to do a lot of row operations on variables, right? Which could be tedious, right? So now with this concept of the dimension of a vector space, right? The aim here is to make that process go much smoother, much quicker, right? And that is in our textbook what this theorem, Theorem G, which the author calls the Goldilocks theorem. And the term comes from it being just the right amount of vectors in a basis, right? So let's switch over here to our textbook and look at what the theorem states. Okay, so Theorem G states that suppose that V is a vector space of dimension T, and let S equal to the sets V1 through Vm be a set of vectors from V, then the four possibilities or the four conclusions can be made, right, depending on where I am at. If M is greater than T, then S is linearly dependent. All right, that's it, right? You don't need to know anything else, right? If the number of vectors is greater than the dimension, automatically linearly dependent. If M is less than T, then S does not span V. And again, this states nothing about linear independence or dependence, right? We do not make a conclusion about that. Okay, we just know that it does not span V, right? Too small, all right? Or number one, too many, right? Too big. And now the third and fourth conditions are where we are just right? If M is equal to T and S is linearly independent, then S spans V. If M is equal to T and S spans V, then S is linearly independent. Okay, so here let's kind of review what this is stating here. Okay, so here we have a vector space, right? Vector space V, and the dimension of V is T. All right, and we're told that we have a set of vectors S to be V1, V2, Vm, okay. Okay, and now here we have the first two conditions, right? The first one, right, M greater than T, S is linearly dependent. It may span the vector space, okay? So again, right, as always when reading these theorems, right, let's be careful that we interpret what it's telling me and what it's not telling me as well, right? What we can deduce from what the theorem is stating. All right, so here S is linearly dependent, right? It may span, it might be a spanning set. That this theorem doesn't aim to answer that question. Okay, So just keep that in mind, right? Keep that in mind and understand that those are two separate concepts, right? When they come together, linear independence and spanning, that's when we have a basis, right? That's a special set. Okay, but here, n greater than t, S is linearly dependent. Maybe a spanning set, I don't know. That would require some more investigation into our set. All right, the second thing that could happen, M could be less than T, right? Now, in this case, if that is true, then S does not span V. But again, as we can say, it might be linearly independent. I don't know, right? This doesn't tell me that, right? It just tells me that I conclude that it does not span V. And again, maybe Li. That would require, again, more investigation, right? And we know how to do that, right? We can check if a set is linearly independent. Okay. All right. Now, in the other case, here, we have 3 and 4. Right? So here we have when M is equal to T. Right? And, here we have two conditions here. And S is linearly independent. Then S spans V. Here we have M is equal to T and S spans V. Then S is linearly independent. Okay, so here what we have is actually an equivalent statement, or we can put both of these two together here. When M is equal to T, then S is linearly dependent if and only if S spans V. All right, so what that means here, what this is going to allow us to do here is that we can check for one thing, all right? So what that means is once you have exactly T vectors, the dimension of the vector space, checking either condition gives you the other for free, is what this is telling you, right? So if you know that this is true, M is equal to T, right? So the size is just right, all right? And you check that it's linearly independent, then it spans V, right? You get that from this theorem, right? That conclusion here, right? So here, once you know this is true, you check linearly independence, and that's all you need to do. Then you get S spans V from that operation. If M is equal to T, you can check if it spans V, and then that's all you need to do to get your linearly independence, because I already know it is just the right size. M is equal to T. Okay, so usually what we'll focus on is showing linearly independence. Right? That's a much more straightforward operation. So usually we'll stick to first verifying the dimension if we don't already know it beforehand, right? And making sure that I have a set of the correct size, and then making sure that it is linearly independent. And once you do those two things, then it spans, right? You don't need to do anything for the spanning part other than check these first two conditions, that you have the right amount of vectors and that it is linearly independent. Okay? So, for example, if we are dealing with a set P3, right, so polynomials of degree 3 or less, then I know that the dimension of this polynomial space is 4. Okay, and we saw from our standard bases that it had 4 vectors. All right. Now again, if we didn't know that this was a basis and we were given the set, then we would check for linearly independence. Right. I know the dimension is 4. There's 4 vectors here. If I check that these are 4 linearly independent vectors, then I don't need to check the spanning part, because the theorem G guarantees me that it will span. All right, so any other set, right? So let's say I had a set that was 2 minus x, 3 minus x squared, 2 plus x cubed minus x here. And let's see, how about x squared minus x cubed. So if you have a set like this, you can determine, okay, well, there's 4 vectors in here, so the size is just right. All right. The only thing to check would be linearly independence. Okay. Now, if the set was let's say this set, right, 1 minus x, 4 plus x squared, 4 minus x cubed, right, then this is not enough vectors, right? So I don't even need to bother with checking any of these other conditions. Here, I know that the theorem G tells me that this does not span V. Now, it does not say, again, does not span V. In this case, V being P4, or P3, excuse me. There's just not enough vectors in there. Okay? Now, if I go ahead and do check and I realize that these are R3 linearly independent, I mean, it still doesn't span it, but I can add another vector to it. Right? I can add one more vector to make it a basis if I properly choose it, so that I have the 4th one is linearly independent among the whole set of 4. Okay? All right, now, this is for vector spaces. Now, in terms of subspaces, we have, and the dimension of those, and here, a theorem in our textbook addresses this situation here. Okay. So theorem E or PSSD, proper subspaces have smaller dimension. And it says, suppose that U and V are subspaces of the vector space W, such that U is a proper subset of V. Then the dimension of U is strictly less than the dimension of V. All right. So proper subspace, subset, meaning that it is not the whole set. Right. So the dimension of any subspace of V will be less than V. So for example, so theorem PSSD. Okay, so here we have that, let's say U is a subspace of V, with U being a proper subset. Okay, so that's what this notation here means. Proper subset, if you think of in terms of the Venn diagram, because if we say subset, the whole set V is a subset of itself. When we say a proper subset, if we think of V here, then U does not contain all of V. Okay, so if that's the case and U is a subspace, then the dimension of U will be less than the dimension of V. Okay, a good way to think of this, if we think of at least geometrically, right? If we think of R3, our Euclidean 3-dimensional space, right? We can have, so that includes 3-dimensional space. We can think of subspaces as planes that go through the origin, right? The dimension of that would be 2, right? If we think of R3 as being, here are standard bases. Right, we can think of simply the xy plane. Excuse me. Let's call this U, to be the span of simply the vectors 1, 0, 0, 0, 1, 0. All right, so we can think of this like the xy plane in three-dimensional space, right? So a subspace here, dimension 2, right? So we see it's strictly less than the bigger space that it lives in, okay? And similarly, right, not geometric, but if we look at the matrices, if we define U to just be two by two matrices where we have numbers on the diagonal, and off diagonals there's 0, so AB is any real number. Right? A and B can also themselves be 0, but they can also take on other values. Right? This is a proper subset here, and as we see here, we can generate a matrix basis with two matrices. The basis for U, and you can see, can be the right. So we know that the dimension of the 2 by 2 matrices is 4, right? And we can see the dimension of U is 2, right? Strict subset, dimension will be strictly smaller, all right? So here, theorem G is the workhorse of this section, right? It's kind of what all was building up from defining the basis, right? Now the properties here, it tells us, right, that we can just essentially, knowing the dimension, we can now reduce the problem of determining whether a set is a basis by checking for linear independence. Spanning as well, but I think the more straightforward approach would be to look at the linear independence of a set if you know the dimension of it.